Thank you for inviting me to take part in this series, especially to go in tandem with Maggie, because these two talks are very closely related, as you'll see. Everybody knows what thermal subsidence is. That's the long-term creation of accommodation of thin lithosphere as it re-equilibrates thermally. And in the last 10 to 15 years, we've also learned a lot about dynamic uplift and subsidence. And these vertical motions of the lithosphere are largely unrelated to thermal subsidence, and therefore they can happen at the same time. And that's what I mean by dynamo-thermal subsidence. There are always two components of the total. So today, I'll try to explain what I mean more by that. And we will also look at the deposition of very thick, short-lived sag salt sections above little faulted base salt or top rift unconformities as magma-rich rifted margins move off incipient lines of breakup. All right, this is not advancing. Okay. Right, so what's dynamic topography? I think everybody here probably knows, but here is an oceanic plate forming, cooling, thickening, and subsiding, and superimposed in color are areas of positive and negative dynamic topography. These overlie zones of upwelling mantle or downwelling mantle, and it's a real force. And I hope you can appreciate that if we removed this force, then this area here would collapse or subside, and that would also be a dynamic subsidence. So the removal of an added force is also a dynamic subsidence, and that's a key to this talk. So we're going to focus on this little box over here, particularly the left arrow here that points down back to the area of dynamic neutrality or isostatic balance. So we can have dynamic elevations up to about 2 kilometers or depressions down to about 2 kilometers. But we're going to focus on this quadrant right here, where we're talking about the dissipation of a dynamic elevation in early post-rift or late syn-rift time. Okay, just a word about magnitudes. This comes from Mackenzie himself, along with Crosby, happily accepting more than 1,500 meters, all the way up to 2,000 meters of dynamic elevations in several of their examples around the world, this one in Hawaii. Okay, now let's go to an onshore section. Here we have a beautiful map of an area of dynamic topography and erosion, producing a regional top rift unconformity across this area of Ethiopia. There's also a regional dynamic elevation. This regional dynamic elevation dominates the tectonic substance of the main Ethiopian rift. And you can see the well-developed rift right in through here, and in cross-section, you can see it here. So here we see the dynamic elevation is dominating the local syn-rift tectonic elevations. And that's very important. And then outside of the area of dynamic elevation, the flanks of the dynamic elevation are getting onlapped by eroded material. Here's another depiction from the same area, section DD. You can see that there is positive topography in an area where the moho is less than 20 kilometers deep. So it would not appear that this area is in isostatic balance. Okay, this map more generally shows the region according to Facena et al. 2013. These contours show the magnitude of dynamic uplift according to them. And what's important here, among many things, is that dynamic topography affects all other topography by up to 2 kilometers. So we have elevated rift flanks and also areas of shallow seafloor spreading. Now, the slopes of these highs are often gentle, but dynamic gradients do reach 2.5 kilometers over 400 kilometers, or about 625 meters in 100 kilometers. And we can see that gradient down here in section AA. I won't tie it in very well later, but we need to keep in mind that dynamic elevations can have these slopes as steep as what we've just said. Okay, so now let's talk about modeling. when people try to restore margins, and in this case, a magma-rich margin, I would just ask the question, why don't we get restorations that look anything like today's modern examples? I think the reason is that they over-rely on isostasy, and they are forgetting about the component that we would now call dynamic elevation. So I would argue that these are still positive features in these early stages, and they have yet to collapse through sea level when they can start to accumulate sag sections and salt, if it happens to be in a sag salt basin. In contrast, when we go to places where we do have vertical control on what the lithosphere is doing, such as in the North Sea, we can see that the magma-rich rift phases are accompanied by strong tectonic uplift. And this would apply to the Viking, Central, and Moray Firth basins. Another way to look at this is to look at examples such as the Newark basins of eastern USA. And Martha Withjack has done a beautiful job looking at vitrinite reflectance and other thermochron data, which suggest up to 6 kilometers of syn rift uplift in erosion of these Newark basins. She gets the data from what's left of the basin, and then she can reconstruct what the basins must have looked like at the time of deposition. And you can see that the camp horizon is shown in purpley pink here, and it's part of the last phase of deposition on top of these rift basins. And then what's interesting is that the eastern continuations of these basins are onlapped by the early Jurassic marine section, and the topography is already gone. It's already been eroded. So this is a good explanation for what's happening, is that there's a syn rift dynamic uplift and erosion associated with the camp magmatism. So what about the rates of dynamic elevation change? If we just take a piece of lithosphere and put a plume under it, we will get an uplift. But if you turn the plume off, it'll take a long time for that elevation to dissipate. And that's because you're basically looking at a thermal subsidence type of situation over 30 million years, and that's not going to be very important for local stratigraphic development. On the other hand, if the plate is moving over the plume, we can take an area that has been uplifted by dynamic topography, and we can move it off the plume quite rapidly, and we can have a 200, 400, 600 kilometer separation between the area of subsidence and the plume. And so we would have a dynamic subsidence that's taking place here, well removed from the original position of the plume. Now, if we can kill 1.5 kilometers of dynamic uplift in maybe 10 or 15 million years, that would lead to a dynamic subsidence which is faster than thermal subsidence of newly thinned continent or new oceanic crust. In other words, this type of dynamic subsidence can outpace thermal subsidence of post-tectonic settings. So let's look at this little cartoon here. We'll try to apply this to a rift now. This would be a magma-rich rift setting where we have an active zone of rifting. This can be largely igneous crust. It can be intruded continental crust or hyper-thinned continental crust. I don't care. But with the extension, those rift zones will move off into a zone that I will call rifted. And that is where we get the deposition of sag and salt sections. So these sections shown in yellow are places where we can predict both dynamic subsidence and also thermal subsidence. They are post-kinematic, post-tectonic, and late in the rift process. And relative to the continents, what's happening is the rifting is migrating away from the continent. But if you think about the sag salt sections, they are being deposited in the wake of the zone of active rifting as the continents pull away from the position of the plume. So again, we can get large dynamic subsidences taking place faster than thermal subsidence in these two basins, and we can get incredible rates of driving subsidences here to account for sag salt deposition. So now let's try to apply this to some of the salt basins. There are two sort of generic types of models. There's the air-filled hole model where the accommodation predates salt deposition.
James?
Yes.
It seems your slide is not advanced.
Uh-oh. Really?
Yeah, now we see it, yes.
Okay, now I'm looking at the two cross sections.
Correct.
Okay, right. So here's an air-filled hole, and the story here would be the basin fills up from bottom to top. So the youngest salt should be on top. I would just like to point out to this crowd, since you probably don't know, the oldest strontium age we have for evaporite deposition around the Gulf of Mexico takes place up here. Linton Land determined this on the Werner, or the lowermost evaporite section, and it's 171. It's the oldest number we have from any of the Gulf of Mexico data, which normally ranges from about 169 to 165.
James, you're now at 10 minutes.
Okay, thank you. Another type of model is that we have some sort of rapid subsidence taking place after the primary tectonic extension has occurred, and this has to happen behind a sill. And I've written papers about a process that I call outer marginal collapse. Other people have offered different models for how this can happen, and I won't go into those. So these are sort of two end members that we're trying to sort out. Let's just look at a couple of sections now from the Sao Paulo Plateau and also the Gulf of Mexico. I want to point out three things about both of these sections. These two basins have three primary things in common. First, the Sin Rift was magma rich, as you can see from the SDRs in the Gulf section at the bottom, and also the fact that the Sao Paulo Plateau is largely an igneous or oceanic plateau with very little evidence of continental crust in it at all. In my opinion, this is an oceanic plateau like Iceland, which happened to be situated between the Brazil crust and the African crust at the time of initial extension. Secondly, the rate of accumulation of the sag and salt in both areas is faster than can be explained by thermal subsidence alone if sedimentation were occurring near sea level. Thirdly, we have very little sign of tectonic extension taking place, certainly in the Gulf of Mexico and in the Sao Paulo Plateau, everywhere west of Tupi. Now so what that means is that we cannot blame this rapid subsidence on tectonic subsidence, on active rifting. Now that statement is not true for the outer portion of Sao Paulo Plateau, where the basement, which I think is pre-existing oceanic plateau, is strongly faulted and salt deposition keeps pace with that faulting. So there is a component of tectonic subsidence going on out here. But let's look at this section a little bit more. This area of strong post-plateau rifting continues laterally into a zone where no one has ever been able to determine the existence of crust. There's a good case to be made that this is exhumed mantle. So even though we had a magma-rich Sin Rift, we have a magma-poor period of time, which might match the time of salt deposition prior to the onset of normal seafloor spreading. The same arguments can be made for the Gulf of Mexico. So some simple cartoons. These are the busy ones with all of the igneous ages shown on them, but we have a plume time shown in this reconstruction between Angola and Brazil. That's late Hotterivian. We have Sin Sag, which is shown in yellow, which is early Aptian, late Berriasian, early Aptian. And then C would be the time of salt deposition, the basinward limits of which are these bold purpley pink lines that you see here. So what's happening? We have the plume activity taking place early on, but that also retracts to the southeast relative to Brazil. And what we have, according to our model, and is supporting our model, is that the sag and salt deposition takes place in the wake of the plume as it moves relatively away from Sao Paulo Plateau. What's actually happening is that Brazil is moving to the northwest from the plume in the mantle reference frame. But relative to the continent, the sag salt deposition takes place in the wake of the plume. Same thing happens in the Gulf of Mexico. Here we have the area affected by camp magmatism in the earliest Jurassic. Then we go to the middle Jurassic, which is the time of salt deposition shown in this really vivid pink in through here. And by that time, the area of plume magmatism is restricted to this area in the Eastern Gulf, as Maggie said, And eventually by the late Jurassic, that retracts farther and ends up running down the Bahamas chain into the early Cretaceous. So we have in the Gulf of Mexico, this prediction for an eastward retraction of the plume. But again, what's happening is that it's the northwestward flight of North America over the mantle, which is giving rise to this relative separation from the plume. And what we see is the deposition of sag and salt in the wake of the plume. So going back to the GOM, I just want to compare this with an eastern GOM section, which is also in our paper. In the west, there's absolutely no sign of faulting until you get right near the edge of the oceanic crust, to blame on tectonic deposition during tectonic extension during salt deposition. In the eastern GOM, if we can assume that the salt marks a timeline, then it's very clear that the rifting is younger in the east and the salt is rifted. And we can see that in this paper and a couple of others as well. And I think Maggie will show that in her paper when it gets accepted. So we have an eastward younging rifting and
hi, James.
okay,
your time is now
I'm
up. If you can help.
So in summary of all this, what we have is an area of uplifted syn rift deformation, active extension, magmatism. There's lots of erosion of rift shoulders and infilling of the basins. And then that moves away from the side of the plume. The plume will be fixed to the right side here. So this crust in gray, which is non-specific in terms of petrology, moves to the left, and it starts to go into this zone of thermal plus dynamic subsidence. So we get the sag above a smooth top rift unconformity, which has been penoplaned up in this situation here. And then we get the salt above that. The Gulf of Mexico story stops in this cross section, but the Brazil story continues into this one. And we have salt being deposited above active rifting and then break up. So if I could cut anything out, this would be it. But I just want to remind people what happens when we don't have thick sag and salt section to keep pace with this rapid early post-rift subsidence. We get rapid rotation of SDR sets, as you can see here, and an angular onset of the subsequent marine section. That means that this rotation basinward has to happen really, really fast because it's hardly recorded by sedimentation at all. Okay, so we can take the two components. There's a thermal component shown in red. That is related to the T to the 1/2/3. We can add an estimated amount of dynamic subsidence, which is in blue, and the two subsidence can sum to give us the total combined dynamo-thermal subsidence. Now, what's important here is a dynamo-thermal subsidence of 2 kilometers can give us 6 kilometers of thick sag salt section in the absence of tectonic faulting. And if we can find places where these sum up to 3 kilometers of driving subsidence, we can explain a post-tectonic section that's as much as 9 kilometers thick when you also consider sedimentary loading. So the main takeaway is thermal subsidence will always be accompanied by a dynamic component of some rate, which is why we coined the term dynamo-thermal subsidence. It has two components. Sometimes they work in tandem, sometimes they fight each other. When they work in tandem, early post-rift dynamo-thermal subsidence, as margins move off plumes or mantle convection cells, can produce accommodation that is so quick that the salt accommodation need not predate salt deposition. Salt deposition can occur near global sea level. And there are lots of arguments for that, which I won't be able to go into. Now, this is not proof that all salt basins form in this way, but it looks to us from the peripheral data that both the Gulf of Mexico and Sao Paulo Plateau did form in this way with salt deposition near global sea level. Further, in the absence of thick salt to fill the accommodation, margins can drown to abyssal depths with little record of the drowning process. And I put this word briançonné in here because there is a place in the Alps where we have rapid drowning right after rifting, which is not known to be magma rich. And yet we have, within the space of about 80 to 90 meters of sedimentary section, we go from intertidal to deep sea radiolarian oozes. So there's a possibility that this process happens in magma pore sessions as well. I won't go through these. I'll leave them up perhaps you'll be able to read some of them. Thank you.